Hello, physics students. It's good to be back again. I know many of you may be taking AP exams this week, so I want to wish you the best of luck. I know both my son and daughter have them, so I know this is a bit of a added stress on this week. So um, take care and make sure you take time to study and get prepared for those exams as well. All right, we want to move on with our study of momentum. And last time we talked about the conservation of momentum, where the initial momentum of a system is going to be equal to the final momentum of the system. And there was that definition. The momentum after an interaction is equal to the momentum before an interaction. And we used this formula. Now, so far, all the problems we've been looking at have an initial momentum of 0, where both objects were at rest to start. They interacted, they pushed against each other, or something happened. One went in one direction, the other object went in the other direction. So one had a positive momentum, one had a negative momentum, so that the total momentum remained 0. So now we're going to look at situations where the initial momentum is not 0. One or both of the objects are in motion and they come together in a collision. So let's talk about collisions. Okay, so there are two main types of collisions: elastic collisions and inelastic collisions. So, and there are some special characteristics of each. But in both an elastic and an inelastic collision, the initial momentum and the final momentum are equal. Okay, that's key in all of these. So let's first talk about the elastic collisions. In an elastic collision, both the momentum and the kinetic energy are conserved. They remain the same. The momentum before the collision is equal to the momentum after the collision, but also the kinetic energy of the two objects before the collision is equal to the kinetic energy after the collision. That is, the kinetic energy part is not true in inelastic collisions. That's the difference between the two types of collisions. Elastic, both momentum and kinetic energy conserved. In an inelastic collision, only the momentum is conserved and there is some loss of kinetic energy. That loss of kinetic energy comes from either the object changing shapes, whether it becomes deformed, smushed, or whether there's some other energies released: sound energy, heat energy. Some of that kinetic energy gets converted into other types of energy. There are very few truly elastic collisions. Now, some are pretty close, but it's very hard to have a truly elastic collision where you don't hear it, the objects don't change shape. They may return back to their original shape, but there's still some deforming during the collision. So there will be a couple times where we assume it's an elastic collision because it's close to elastic, but there are very few of those that truly are. All right, let's talk about the two types of inelastic collisions. The first is what's called the perfectly inelastic collision. This is where the two objects collide and they stick together. They move off as one object. You see that a lot of times maybe in a car crash where the two objects get locked together and they move off in the same direction. Okay? So in that case, they share a common final velocity. Okay, this common final velocity, we can then just add the two masses together and they move off with the same common velocity. The other type of inelastic collision is just the regular inelastic collision, where they don't stick together. So you still have a final velocity of object 1 and a final velocity of object 2. Okay? But in every case, in every collision, the momentum is conserved. Now, let's talk about an elastic collision. There's one type of inelastic collision that's a specific type. And that's if the initial velocity of the second object is 0. Okay, the initial velocity of the second object is 0. And we're going to talk about 3 specific examples of these and what you think may happen. Okay, so here's a special formula case. If it's this is only true if it's an elastic collision and if the velocity of the second object is 0. The final velocity of the first object is equal to this. Mass of the first object minus mass of the second object divided by the 2 objects added together times the initial velocity of the first object. The final velocity of the second object is 2 times m1 divided by m1 plus m2, and again, multiplied by the velocity of the first object. So let me give you the 3 scenarios. One is when the objects are of equal mass. Okay, so the best example of this, or the closest example of this, would be like 2 billiard balls, the cue ball and a regular ball. They both have the same mass. So when they collide in an elastic collision, what happens? If you're looking at the formula, well, m1 and m2 are equal. So when you subtract these two, they become 0. So the first object stops and the second object moves away with a velocity, well, 2 times m1. And again, m1 and m2 are the same. So this becomes 1. So the second object moves away with all of the momentum of the system. So they come together. The cue ball is moving. It strikes the object ball. The cue ball stops. The object ball moves off with the velocity of the first ball. The second example is when there is a massive object running into a less massive object. The best example of this would be a bowling ball running into a bowling pin. Okay, so the bowling pin has a velocity of 0, and the bowling ball is moving forward. So the bowling ball is much more massive than the bowling pin. So when I take a look at this subtraction in the first one, m1 is bigger than m2. So this becomes a positive number. So the bowling ball keeps moving. Right? The bowling ball hits the bowling pin. It keeps moving. And what happens to the bowling pin? It goes flying away in the same direction of the bowling ball, but at a faster velocity, right? Because the m1 doubled. So this number is going to be bigger than 1, because m2 plus m1 is going to be smaller than 2m1. So this pin goes flying off. So the bowling ball transfers some of its momentum to the bowling pin. The bowling pin goes flying away, and they both move in the same direction. The final example is what happens if m2 is more massive than m1. So let's take our same bowling ball, and this time let's throw a baseball, or even better yet, let's throw a marble at it. Okay, so the bowling ball, much more massive than the marble, but the bowling ball is at rest. The marble is going to come flying in with a velocity. So what happens when a marble hits a bowling ball? Okay, think about it. the marble goes flying backwards in the opposite direction, and the bowling ball might move forward just a little bit. That's symbolized again with this equation. M1, very small, M2, very large. So this is going to be a negative number, meaning this final velocity is going to be negative. That marble is going to bounce off the bowling ball. Now, M2, the velocity of the second mass, M1, very small. So this number is going to be a very small number because the two of the masses added together, is still way bigger than the two masses of the marble. So it's going to make a small number. So it's going to give a small velocity, but in the positive direction. So the bowling ball is going to move in the direction the marble was going, but at a very slow rate. Okay. So this just summarizes all that down here. If M1 and M2 are equal, the final velocity of the second object is 0, and the first and the second object moves off with a velocity equal to the first object. If M1 is bigger than M2, the bowling ball hitting the bowling pin, they both fly off in the positive direction, or the direction that the bowling ball is rolling. The bowling ball slows down a little bit. The bowling pin goes flying off very, very fast. And the final case, where a large object is hit by a small object, the small object bounces off and travels in the opposite direction, and the large object moves in that positive direction, yet at a very slow rate. Okay, so that's it for the types of collisions. Remember the difference between elastic and inelastic. Conservation of momentum occurs for both. Conservation of kinetic energy for elastic. Loss of kinetic energy for an inelastic. And the two types of inelastic. Perfectly inelastic, they stick together. And a regular inelastic collision where they do not stick together. Okay, so that's the end of that. I wanted to also thank all of you who took a minute and filled out the survey that I posted last week. Your comments were very kind. Many of you, thank you. I appreciate those. I hope you are all staying safe, doing well. If there's something that you need or questions that you have, please, please, please reach out to me, either through email or post a comment in Google Classroom so we can ask your question. Okay. There will be a lesson assessment that goes along with this short video to go over the types of collisions. The next video, we'll do some problems where we're going to show how we use the conservation of momentum and the types of collisions to do some problems. Until then, stay safe.